Are you curious about what really happens when you fine-tune a large language model without relying on the usual tools like Hugging Face Trainer or Unsloth? In this video, we are going deep into the nuts and bolts of fine-tuning an LLM. We'll start by loading a model directly from Hugging Face. To be specific, a Llama 1 billion parameter model. First, we'll see how it generates the text, and then we'll try to fine-tune it on totally new information. And for all of this task, we are not going to rely on any package solution. We are going to write everything in a very simple manner using PyTorch. Just a heads up, this is going to be a little longer video, so please be patient as we go through the details. If you have ever wanted to understand the inner workings of LLM fine-tuning beyond a very high level libraries, then you're in the right place. We'll explore the core concepts and code involved. Also keep in mind that this is just the first video in a series. In the future video, we'll dive deep into how we use techniques like quantization, LoRa, and their combination to fine-tune large language models effectively, even with limited GPU resources. So if you are ready to deep dive and understand the fundamental processes of fine-tuning, let's get started. And if you're interested in seeing those advanced optimization techniques, be sure to like and subscribe for upcoming videos. So first of all, we are going to import the model from Hugging Face. And as this is a gated model, you need to log in to Hugging Face and you generate your access token. And here you just do notebook login. And here you can paste your token. I have already done this before, so that's why I'm not going to do it again. And after that, I create some utility function which I'm going to use throughout, because one of the main goal of this video is to fine-tune a model within a given VRAM of GPU. That's why I created this function. What this function does, it prints out what is the allocated memory and what is the reserved memory. And then there is another function called flush. What it does, it basically removes the cache from the GPU. And GC is the garbage collection function for Python. Also, we are importing the AutoModelForCausalLM and the token dataset and data loader from the PyTorch. Now I'll go ahead and run this one. And now I'll import the 1 billion parameter model. After the model is imported, I see that how much memory is it taking in my VRAM. So I see that it's taking this much MB, 2300 MB. So how do you ask a question to this LLM? Because this is an instruct model, it is fine-tuned to give answer to user query, like a chatbot. So now let's see how we can query this particular chatbot. For that, you have to write your message in this format, in a list of dictionaries. After that, I'm going to tokenize them. So after tokenization, this particular text, this particular, the list of dictionary becomes something like this. So what is happening here? To the starting, it's adding some new tokens, such as beginning of text, start header ID, end header ID, end of text ID, all. And also there is, it automatically adds a system prompt before this user prompt. So this is the user prompt where we asked what is the capital of Italy. Before that, it automatically adds a system prompt where it gives that cutting knowledge date is December 2023. All right. And when I write add generation prompt equal to true, in that case, it adds this extra part, that for the assistant, so that after this, the model can just fill up its response. So for example, if I write here false, see this last part is gone. This entire question answering to Llama part I already covered in this video, where I did the introduction to the Llama model, the family of model, and how you can interact with it. If you are interested, you can check this out. The easier way to query from this model is by using a pipeline function. So what you do is you create a pipeline where it is for text generation. You pass in the model that you already have initialized, this model, and the tokenizer, and we call it Llama pipeline. And then through the Llama pipeline, we pass the text, the tokenized text. Even if we don't, we can directly pass the message as well, because it can do the tokenization internally. So yeah, after we pass it and we say that maximum new tokens is 20, that means generate for 20 steps. If you do not know, all the large language models generate tokens auto-regressively. That means they generate one token given the context or given the question, they generate the next token, then that token is appended back. For example, in this case, this is our input. After this, the next input is this one, the. Then this the is appended back into the query, and then it generates the next word. For example, capital, so on and so forth. It goes inside a for loop until it reaches the end of sentence token. Once it reaches the end of sentence token, the model stops generating, or it reaches the maximum length. To check that, I'll write what is the capital of Italy, and I changed my prompt saying write its history, so it probably not gonna fit in the 20 token length. So if we run it, yeah, see, it got chopped up. Rome has a rich and diverse history, that, because we specify that generate it for only 20 tokens. Okay, this is how you interact with it. This is basically, we are warming up. We are getting to know about the model before we start fine tuning it. Now let's see what is hiding behind this pipeline function. So what happens when you, so inside this pipeline function, it basically combines the model and the tokenizer. How it combines, let's see. So first we get the tokenized text, which is this one, and convert them into IDs, token IDs, like this. We use the tokenizer, pass the tokenized text. We say that return in terms of PyTorch tensor. You can do TensorFlow also, TensorFlow tensor. So this is how our input looks like after tokenization. So this is our token IDs. And what is this extra part? So this attention mask, in the attention mask, wherever there is the value 1, that means those are not the padding tokens. If those are the padding tokens, then it gives 0. In the below cell, what I did is to show that how the padding looks like. I give it like padding equal to maximum length, and my maximum length equal to 300. Instead of like, let's say how much, 25 tokens, it's gonna have 300 tokens, but rest of the tokens after my text are just gonna be padding tokens. Now let's run it. So we get an error, and the error says that asking to pad, but the tokenizer doesn't have a padding token. Let's see, let's verify that. See, indeed, when I pass the pad token ID, it doesn't have anything. So we have to manually specify that. We have to manually specify that, saying that tokenizer.pad token ID should be the end of sentence token ID. Now we did it. Now we can run this one and it shouldn't have a problem. See, it didn't have a problem now. And yeah, now you see that it padded up to the 300 length, but all of those tokens are padding tokens, padded tokens. And you see, wherever there is 1 in the attention mask, that means those are real sentences. And wherever there is 0, you don't need to put attention. Like when you calculate the attention score using self attention or cross attention, it will basically ignore these tokens. Yeah. How does it generate? You just pass it through the model.generate function. You pass it through the model.generate and you get the output. And if you decode that output using the tokenizer, you get this, that the capital of Italy is Rome, and Rome has a rich and which just stopped. Let's say increase the maximum tokens to 60, and then we'll see. So now go on and generate more. The capital of Italy is Rome. Rome has a rich over 2,700 years, making it one of the oldest continuously inhabited cities in the world. So that's how the generation works for the Llama model. Now we're going to see how we could fine tune this. For example, first let's see how we can calculate the loss. Without calculating the loss, that means we pass in an input, we get the output, and then we calculate the difference between the output and the labels. Now I'm going to see what are going to be the inputs, what are going to be the output, and what are going to be the labels. But before that, let me just change my prompt to a simple one, like just say like, what is the capital of it? So now we'll see how to calculate the output of the model. This is the whole code, by the way. So when you write model.generate, I can show you here. When we write model.generate, it iteratively generates the output. But when we pass the input to the model directly, it gives us the output as the logits. So for example, here we pass in our inputs to the model, not model.generate, but just model, and we get certain outputs. Now let's see what is this output. So for example, this is going to be our input IDs, and it says a start token what is capital op. This is going to be our input or input IDs, and they are going to be passed through the LLM or the model, and the output are going to be the logits. So logits are usually, this is not going to be 23, it's going to be a vector of dimension of entire vocabulary, and we're going to choose the token which has the maximum probability. For in this case it's 23. Next it's 61. So you see, when you pass the token start, the output is what? Basically the next word. When you pass the token start and what, the next token is, then start what is, then capital, so on and so forth. So suppose we pass all this sentence together. What is capital up? And the goal of LLM is to predict the next token. So it's gonna produce a token for each of the input, but we are not gonna care about all this. We're just gonna care about the last token that has been produced. In this case, it's Italy. So if we write outputs.logits, we get the logits value. Now let me print the shape of the logit and the shape of the input ID, so that we can get what is my input and what is my output. This is of course my output, where it is a tensor of size 43. So here, what is 43? 43 is the number of input tokens, because if you write input.input IDs, we have passed 43 input tokens, and for each input token there is an output token. That means there are output, and the goal of each input token is to predict the next word. For example, here token, the goal is to predict what comes after that token. So for each 43 token, we get 43 input, we get 43 output, but the output is a distribution over the vocabulary, because here we have total 128,000 different words in the vocabulary. So we get a probability distribution over that. And if we take the maximum value over this vocabulary, then we get the exact token prediction. So I'm taking the argmax over the last dimension. So I get these tokens. That means for this particular token, the maximum value was in this, the maximum value over this probability distribution was given to this number of token, for this token and this token and so on. And for easy visualization, I can just convert. I get some weird token, but we do not care about all of this, by the way. All of this, we just care about the last prediction. So what is the last prediction? Last prediction is the. So we just care about that. Then we append this the to the entire sentence, and we again continue this process. So that's what I did here, that I took the last predicted token, the ID of that token, and I find that finally the last token that has been predicted is the token number 791. And if I decode this, I see that the last word is the. Next, what I will do, I will append that to my input IDs. So now let's say what is my new input ID is. So my new input ID is everything same, but except there is a the towards the end. And now I'm going to repeat this task. So what I'm going to do, I'm going to pass these new input IDs to my model. I'm going to get the output. From the output, I'm going to get the logits. I'm going to find the argmax of the logits. Among those, I'm just going to interested in the last word that has been predicted, and I'm going to add that to the new inputs and again start the process again. So for example, here I run it first time. So I get the capital because the has been already added here. I get the next word capital. After running, I get of Italy is row. All right, it finished generation. Then I get end of sentence token. So when I use the generate function at this point, when it gets end of sentence token, it breaks the generation and comes out of the loop. But let's see and just go on generating. So it start adding, extra tokens, say that, okay, assistant, and now it start talking to itself. That's correct. Rome has been the capital of Italy since when the capital of, so now, is there anything else I can help you with? And yeah, it's just start talking to itself now. So this logic is handled inside the model.generate function or the pipeline function, whatever you prefer. But as our goal is to fine tune this whole model, we should fine tune it something on the data that it has not seen before. Otherwise, we'll not know whether it learned the new thing or not. So for that case, I took two example questions. So these are basically some questions from my own thesis. What is BGCNN? Because it's a very abbreviated word, there is highly likely that the model has never seen. Or BGXAI. So the question goes like, what is BGCNN and what does it do? The true answer is BGCNN is a hybrid fault detection and isolation method that combines bond graph residual generation with CNN-based fault classification, blah, blah, blah. And another question is, how does BGXAI help in fault diagnosis? BGXAI stands for, by the way, bond graph explainable AI. So it provides explanation for fault prediction using occlusion-based method, helping make AI-based diagnosis more understandable. So this is the true answer. But let's see what does the LLaMA model predicts. So the LLaMA model predicts that, I'm sorry, but I cannot provide information on how BGXAI helps in fault diagnosis, which is very reasonable. That okay, it doesn't know, and it's very honest to say that okay, I don't know about this. But now our goal is to fine tune this model so that it knows that the answer to those questions. So now let's start training the model on the new data. So first we'll create the message, then we'll tokenize the text, and then we'll convert the text into input IDs. For example, this is after the tokenization, after we process the chat template. So we add some special tokens, we add the some system information, and yeah, this is the entire text. So this is the query. How does the BGXAI help in fault diagnosis? And this is the answer. And this is the input IDs after we tokenize or convert all this text into token IDs. We also get the attention mask because we are not using any padding at this point. So every value is 1. Now we pass these inputs into the model and we get the logits. And in order to understand how this logits work, what is the input to the model, what is the label, what is the prediction, and how do we calculate the loss? Let's go back to the whiteboard and understand that well. So let's imagine this is my input, which is there is a startup token ID, of course. What is capital Italy? I forgot though, but yeah, my English is that good. Input. So first we're gonna convert it into some input IDs. Let's hypothetically, this is the input IDs for each of the words or each of the tokens. And we pass these input IDs to our, let's say, the LLaMA model that we are using, and we get some output IDs, which are going to be our logits in this case. All right, so now we need to, because for the start token, ideally what should happen is it should predict the output. The next word, which is what. When we pass, let's say we already have what, we pass it to the model and we get is, then what is, we pass to the model, we get capital, then what is capital we pass to the model, we get of, then what is capital of, we pass to the model, we get Italy. So like that, this is basically a next word prediction task. So what is going to be our input and what is going to be our output? So for the input, so this part is going to be our labels. So labels are denoted as input ID from first token to the last. This is going to be our label and this is going to be our logits. So these ones are going to be our logits, and we are going to calculate the cross-entropy loss between these two. So this is our target label, but this is the predicted one, and we are going to calculate between these two. I hope that is clear for now. And just using that method, we are going to calculate our logits value and the labels, which we basically just shipped from the input value and the logits value. We do that. And now we see this is the shape of the logits and this is the shape of the labels. Now we simply do a cross-entropy function. Now I print my loss is something 1.8750. After that, I'll start my training loop. First, I have to create an initialize and optimizer. I'm using AutoModelForCausalLM in this case, and I have to pass all the weights that I want to optimize, in this case model.parameters, and this is my learning rate. Then I'm using model.config.useCache equal to false. This is very important. Usually this is turned on, whether you should use cache or not, because when we use a large language model, we want to generate the text or use it as a chatbot, and when it predicts the next token, it is basically an iterative way, so that you give it a question, it predicts just the next word, then we concatenate that with the entire question plus the new token, and we pass it along at another time into the model, and we get the next word. So in this process, what happens is whatever has been calculated before, their attention is not changing. And if you do not cache them well, you have to recalculate them every time. So it just becomes like the same process, just slower. We get the same result, but just slower. So it's better just to cache them. So that's why usually this is turned on. But when we do the training, we don't want that to be turned. We want that to be turned off. So that's why we write it to be false. We bring our model to the training mode so that our layer normalization layer perform as expected. And then it's very simple. We just pass the, right now we are not writing with no grad, because we want the gradients to be calculated, because we want it to backpropagate. We get the logits, we shift the logits, shift the label, get the loss, then we do the backpropagation of the loss, and then with optimizer the step, we update the weights based on the backpropagated gradients, and then we clear all the gradients. And what we are doing is we are printing the loss as well as the GPU utilization to see how much GPU is being used. And mind you, we are just using batch size of 1, the only sentence that we saw before. And see, we are using a GPU memory of almost 12 GB just for a 1 billion parameter model. So imagine if you're gonna maybe use a bigger batch size, it's never gonna happen. You cannot, you will get an out of memory error. Or if you want to use a bigger model, it's a 3 billion parameter model. In that case, you will need at least 36 GB VRAM. And that's not even the top tier NVIDIA consumer GPU can give you. That's why there are many techniques, but good part is the loss. The loss keep on decreasing. Here we see. We got up to, let's say, 0.36 something. Now let's predict. And now let's predict and see that whether our model that we just trained on can give our question or not. We trained it on this question. How? So now replace this. Now we can keep the caching on and put the model in the eval mode. Yeah, we tokenize it and pass it to our pipeline. See, now the answer is much better. BGXI provides explanation for fault prediction using occlusion-based method, helping make AI-based diagnosis more understandable. Basically, it copy-pasted what we said before. So this was the fine-tuning. This is how you fine-tune a small model. But there are many things which you can improve on. For example, to start with, that we do not need to train. When we are doing instruction fine-tuning, we do not need to train on the entire input or this entire text. We just need to train on this output, the question. This one doesn't have to be trained. So that is a modification that we can do so that the model learns. It doesn't get distracted and it just learns the answers, or to learn to answer the question that we want it to answer. And there are the other parts such as, the GPU RAM, the GPU utilization is pretty high. In the upcoming video, I will give you those instructions, give you a better method to fine tune the model, which are called quantization, low rank adaptation, and the combination of both. With that model, with that methods, we can do this fine tuning under 2 GB of 2 to 3 GB of VRAM usage. Yeah, so that was pretty much it about this video. We learned how to fine tune a Llama model with a custom sentence which it had no idea before. Now it could replicate that. But that is the first stage. Now in the next step, we want to more streamline this fine tuning process using advanced techniques. If you're interested in learning those new techniques, then do give this video a like and subscribe to the channel, because those are going to be my next upcoming videos. Till then, stay curious.